Mayo the Fourth. I'm part of the technical and design promotions team of ABB Electrification here in the Philippines. So first of all, I'd like to wish everyone that everyone's staying safe, staying healthy at this very challenging moment that we are in right now. Um, this will be a very straightforward discussion. I'm pretty much sure uh, most of you know what a miniature circuit breaker is, but uh, this will be most of you this will be a refresher. So I'd be discussing the selection criteria for miniature circuit breakers, but with emphasis with the standards of IEC, with the international standards of IEC 60947-2 and IEC 60898-1. Okay, so here is I've subdivided the presentation into several topics. So basically, I'd be discussing an overview, the requirements for MCBs, how an MCB functions, of course, the international standards, the difference between 898-1 and 947-2, and multi-standard circuit breakers, which once we use multi-standard circuit breakers, which of the standards will we use? And then, of course, probably an example of a selectivity or why selectivity is important as well for final distribution circuit breakers. And of course, specifying miniature circuit breakers and another overview on the MCB solutions of ABB. So this is probably a very short presentation, and uh, if you have notes or if you have uh, time to take note, you can do so. But we will be also giving a copy of the presentation after this. But I think for the quiz later, you'd be taking notes would be of great help. So first would be the overview of ABB solutions for overcurrent protection. So these are the basic uh, offerings of ABB for low voltage overcurrent protection. So I'd start with the miniature circuit breakers, which is equipped with a fixed thermal magnetic release, and then both conforms both with IEC 60898 and IEC 60947-2. Another solution would be for the sub-distribution panel boards, or what we usually use the molded case circuit breakers. These can be equipped with a thermal magnetic release or an electronic release for LSIG or communication interfacing. So this is compliant with IEC 60947-2. And lastly are the air circuit breakers or the power breakers, which are equipped with the most advanced electronic releases and also compliant with IEC 60947-2. So as you can see, from miniature circuit breakers up to air circuit breakers, they are following one standard, which is IEC 60947-2. The only difference is that for miniature circuit breakers, we also have what you call the IEC 60898-1 standard. So I think here in the Philippines, this is a standard that we probably as practitioners we need to know and understand in a way primarily because IEC is being adapted or being used nationwide as part of the design and the specification of buildings or and low voltage power systems. So just to give you an overview, probably just a quick history of how the how we came up with the miniature circuit breaker. So it started with the invention of the automatic fuse, which was done by, or invented by Mr. Hugo Stotz, and it started at started the development 1923, and then the patent was granted to him a year later, 1924, and then of course mass production was done 4 years after the development or after the patent has been granted to him. So this became the what we call nowadays as the miniature circuit breaker. Okay, so Hugo Stotz invented a reclosable braking system, which is nowadays called the miniature circuit breaker. So basically, if you research back, if you research the foundation or the history of miniature circuit breakers, it is actually part of the ABB history or ABB legacy. So first, Stotz MCB with K characteristic was introduced in the during the 1928. This was the first one of the first MCBs introduced to the market. The second generation MCB launched 1948, and then the first 10 kiloamp miniature circuit breaker released 1956. And then of course the miniature circuit breakers for DIN rail, and eventually the first selective circuit breaker in the 1980s, and lastly the modern miniature circuit breakers that we have here right now. Okay, so basically a miniature circuit breaker would function as a during predetermined off overcurrent switch off, and then an immediate it also functions as an immediate short circuit break to protect the wires, and at the same time, which is more I think during the time of the developments is the availability after fault removal, which was not done using fuses. So basically, this was the innovation then. So the availability after fault removal. So this is a very typical block diagram that you can see, which more or less contains the function of a miniature circuit breaker. So it contains a bimetal and a coil, which is the one who sends the signal to the switching mechanism. So later I'll discuss more on these components. So the functional components are as follows. So first would be the bimetal overload trip. So which is basically two metals joined together. These two metals have different temperature coefficients. So and anytime during the operation there's a high temperature or a low temperature or temperature variance, there will be a certain amount of deflection, which would trigger the on and off, or which would trigger the tripping of the circuit breakers. Of course, the toggle, which is the manual interface for manual operation of a miniature circuit breaker. And then, of course, the electromagnetic short circuit trip, which consists of coils and armatures. And the switching mechanism. And lastly, of course, one of the most important part would be the extinguishing system. So this is an inside look of a real miniature circuit breaker. So if you get an ABB miniature circuit breaker, you'd see these components. So in comparison with the earlier illustration, so this is the more real illustration based on ABB circuit breakers. So of course, just to put emphasis, the first would be the bimetal overload trip. So this is number one. And then the toggle, the electromagnetic short circuit trip, this one, the switching mechanism, and of course the arc extinguishing system. So let's go into detail what functions these functional components have in order to complete the functionality of a miniature circuit breaker. So first, let's take a look at the bimetal overload trip. So basically, the bimetal overload trip functions during overload. It's basically as easy as that. So it's, as mentioned earlier, it is composed of two metal strips combined with two different temperature coefficients, wherein uh, it measures mechanically based on the thermal property of the metal. It's the heat dissipated within the strip, and as we all know, heat is correlated with the intensity of current, and of course the duration of exposure for the two metal strips. So if an MCB if the two metal strip or the bimetal strip detects an amount of heat which is correlated to the current intensity at a certain period of time. The bimetal strip gives the signal to the switching mechanism. So as you can see, it pulled this up due to the deflection created by the excessive heat in the bimetal strip. So this would trigger the switching mechanism and eventually the contacts, or opening the contacts. Thus, we have an overload trip. So basically, just remember the deflection of the bimetal depends on current intensity and duration. So of course, the toggle is the main, the manual operating switching device, which forces the contacts together or apart. So the idea is for free tripping release, which is basically an inherent function of ABB miniature circuit breakers, is basically a mechanism that prevents reclosing if the fault is still there or if the fault is still present. So again, this is what you need to look for the specification: free tripping release, and of course the bimetal strip. And then at the same time, for electromagnetic short circuit trip, uh, we have several components. First would be the trip lever, and then the movable armature and the fixed armature. So the movable armature is on the top of the spring, and the fixed armature is on the bottom. So during short circuit or during electromagnetic tripping, this will go down. So there is as mentioned here, there is a fixed and a movable armature, and if the current exceeds the nominal current or the rated current of the circuit breaker, the armature will be attracted against the spring. So this will go down, thus pushing the pushing the switching contact open. So the switching mechanism provides the opening of the contacts. And lastly, breaking of short circuit currents. So basically, as you all know, the most important component in breaking short circuits is the time duration, or the breaking time. So basically, the idea would be the switch off delay must be as short as possible. So the switching mechanism has springs and masses, thus resulting to unacceptably high switch off delay. And basically, what's important here is the hammer trip function of the electromagnetic short circuit trip, primarily because this hastens, or this speeds up the breaking time of the circuit breaker during short circuit anomalies. So the hammer trip is an essential element in limiting short circuit current. So later I'll show you how it operates during short circuit. So this is the arc extinguishing system, which is also one of the more important components within the miniature circuit breaker, primarily because it splits the arc during opening. Because during opening of the arcs, we can't really avoid the arcs in between the contacts. So the idea of the idea of an arc extinguishing system is that it absorbs the arc it extinguishes the arc by separating it into multiple plates with a maximum voltage of 30 volts. So the extinction of the arc guarantees fast, reliable disconnection of the circuit. So here's a short circuit demonstration, and this is the time duration that we have. So during the short circuit, the breaker starts to react. So the hammer trip pushes the contacts apart. This one, it pushes the contacts apart, thus generating a small arc between the contacts. So an arc is created between the moving and fixed contact. So at 1 millisecond, I would see that there's a cloud, a cloud-like picture within the arc extinguishing system. So the moving contact is nearly opened at 1 millisecond. And as you can see, the arc can be clearly seen as ionized gases, or cloud-like cloud-like picture, or cloud-like image within the in between the contacts. which toward uh, or the arc extinguishing system. So this is the arc extinguishing system. Here's the ionized gases produced during the opening of the contacts. So at 1.5 milliseconds after the short circuit, the arc has now left the contacts and is in the extinguishing chamber. So 2 milliseconds after the short circuit, the arc is now in the arc chute here, and the metal plate will divide the arc into small separated arcs with an arc voltage in between the two metal plates of 30 volts. And at 2.5 milliseconds, the arcs are separated into small arcs, and the circuit is finally disconnected. So as you can see, the contacts are now separated. So it's as quick as 2.5 to 3.5 milliseconds, as you can see. So I think this is one of the fastest breaking time for a miniature circuit breaker, 2.5 to 3.5 milliseconds. So as you can see, as mentioned earlier in the overview, there are two circuit breaker standards present in the market right now. One is the IEC 60947-2, which discusses low voltage switchgear and control gear, and the IEC 60898-1, which discusses the overcurrent protection for household and similar applications. So the difference between the two primarily, basically, you'd see here. So the first one would be for 947-2, it is applied in industrial environment and with rated voltage up to 1000 volts up to 1500 volts DC. On the other hand, for 60898-1, it is ideally used for residential buildings and or similar applications. And basically, by standard, 947-2 circuit breakers are usually designed to be used by skilled or instructed people. So these are our RMEs, our electrical engineers, and other licensed practitioners. And then, of course, for circuit breakers designed under 898-1 standard, it's used by unskilled or uninstructed people. So these, as mentioned earlier, this is meant to be used within residential facilities, which are operated by unskilled or uninstructed people. Of course, the two circuit breakers have short circuit protection. The only difference is that for short circuit protection under 947-2, the calibration of the magnetic release is under the manufacturer's prerogative. On the other hand, for IEC 60898-1 standard, there's what you call the standard current settings, which is the B curve, the C curve, and the D curve. So later, I'll show you the difference between the three, and ABB has two other solutions for more rugged applications or more sensitive applications. So for short circuit protection, here's what you'd see in reference to the curves. So we have the B type, the C type, and the D type. Time to trip are the same. The difference are the test current. So for B type, it's tested under 3 to 5 times the rated current of the circuit breaker. So B-type circuit breakers are suitable for resistive loads like water heaters, electric stoves, and etc. etc. For C-type circuit breakers, same trip time, but the difference is the test current, 5 to 10 times the rated current, which is the most typical circuit breaker that we have in the market right now. So C-type circuit breakers are suitable for socket outlets, lighting loads, and motors of smaller capacity. And for D-type circuit breaker, so the test current is 10 to the 20 times the rated current. Same trip time, but the D type is used to protect circuit where there are higher transient inrush currents, typically large motors. So when designing unit panel boards or consumer panel boards, it's ideal to understand the load that the circuit breaker is protecting. So if there's a large motor, if we are going to use a large motor within a facility, we will use a D-type circuit breaker. For typical socket outlets, we use the C curve, and for primarily for resistive loads, we use the B curve. Okay, again, these are circuit breakers, so of course they will have thermal magnetic thermal release as well. So the thermal trip is basically again based on bimetallic strip as discussed earlier. But the difference between the two is that the ambient temperature for 947-2 is tested at 40 degrees, while the ambient temperature for 60898-1 is tested at 30 degrees Celsius. So for 947-2 circuit breakers, there are no rated current limit specified. But as we all know, uh, for air circuit breakers, I think the largest rated current that we have is 6,300 amps. So it depends. So on the other hand, for 60898-1, the circuit breaker rated current defined in the standards is a maximum of 125 amps. Of course, the two still has ICU and ICS, or the ultimate braking capacity and the service braking capacity. The difference is that we are using the ICN for IEC 60898-1. So if we are using a circuit breaker under the 60898-1 standard, we won't find an ICU for it. We will find an ICN. So these still are based on the short circuit fault or the calculated short circuit current that we have on the bus. So it should be greater or higher than the one that we calculated. And the difference is that 947-2 has 8 type testing procedures, while 60898-1 has 14 type testing procedures. So just to highlight the 14 type testing procedures, as you can see here, of course, the marking, the reliability of screws, reliability of terminals for external conductors, protection against electric shock, dielectric and isolating capabilities, temperature rise, 28-day test, the tripping characteristics, mechanical and electrical endurance, short circuit, etc., etc. For the 60947-2, it is tested in 8 type testing procedures as well. As mentioned, temperature rise, trip limits and characteristics, dielectric properties, overload performances, short circuit braking capacities. Short circuit withstand, especially for air circuit breakers wherein there's a required time delay. So we need to also test the short time withstand. And then the performance of integrally fused circuit breakers. So as you would observe, as you can observe, the 14 type tests of the IEC 60898-1 comprises of both the electrical and mechanical properties, while the 8 type testing procedures composed of primarily focused on the electrical properties of the circuit breaker. So again, just to give you an idea, the IEC 60898-1 28-day test. So basically, the circuit breaker is subjected to 28 cycles. So basically, one cycle would comprise of 21 hours with rated current and 3 hours with no load. And the temperature is increased within 5 seconds to a tripping value. So the temperature is measured and the tripping time is also measured. So it's basically a 28 cycle test, but one cycle is 1 day, so it's called 28-day test. Another test procedure under 60898-1 is the glow test, which is according to IEC 60695-2. So the glow test is basically for the insulating body of the miniature circuit breakers, and the external insulating parts should retain position of current carrying parts and other parts of the protective circuit breaker of the protective circuit when tested at 960 degrees plus minus 15%. So again, as you can see, they are also testing the mechanical or the insulating properties of the circuit breaker primarily because it is assumed that for circuit breakers under 60898-1, it's being operated by non-trained or non-technical personnel. So this is the K factor, which is the ratio between the service breaking capacity and the short circuit breaking capacity of a miniature circuit breaker tested under 60898-1. So if you look at a miniature circuit breaker, you won't find the ICS, but what you'll find is the K the ultimate breaking capacity, which is basically there's a K factor in depending on the magnitude or the tested short circuit capacity of the circuit breaker. So basically for the ones for the circuit breakers rating less than or equal to 6 KI, the rated K factor is 1. So for between 6 KA and 10 KA, it's 0.75, but the minimum would be the minimum value is 6 kiloamps. And for more than 10 KA, the K factor is 0.5. So but the minimum value is 7.5 K. So as you can see, you'll not get the service breaking capacity uh, in the markings, but you'll understand it once you check the IEC 60898-1, which is the K factor, which can be used which can be calculated using the K factor. And then let's move forward with the IEC 60947-2. So as mandated by the standard and is derived with respect to the ICU, the ultimate short circuit breaking capacity is in reference. This is the reference of the ICS or the service breaking capacity. So there's a certain test sequence in order to achieve the ICS value of the circuit breaker under 60947-2. Later, I will show you the test sequence once we move forward with the specification of the miniature circuit breakers. So again, there are most of the time there are circuit breakers that you'll find in the market that are both compliant with 60947-2 and 60898-1, which most of the time or sometimes for designers, for consultants, and for contractors, it's quite confusing which standard to use during the buying or during the selection phase of the miniature circuit breakers. So basically, a circuit breaker can withstand a 10 kiloamp short circuit according to IEC 60947-2, but may only have a breaking capacity of 6 kiloamps according to IEC 60898-1. So, so when do we use the 10 kiloamps or when do we use the 6 kiloamp rating? So basically, you'd understand once we go forward with the next slide. But basically, it is required or it is ideal to get the test report, which guarantees that the circuit breakers are in accordance to the required standards. So again, this can be used depending on the location. So as you can see, uh, if the circuit breaker will be installed outside a residential dwelling facility or a residential dwelling unit, we use the IEC 60947-2 or the 10 kiloamp rating. On the other hand, if the circuit breaker will be installed inside a residential facility wherein the electrician or the electrical practitioner has no access, and the only ones who can access it would be the owner of the residential facility, we use the 60898-1 standard. So why is selectivity important in all of these? Basically, if selectivity is not achieved, fault within the residential units may affect the upstream circuit breakers. And most of the time, these are the circuit breakers in the metering panels or inside the electrical room. So in this case, the user will have to wait for maintenance personnel to reset the circuit breaker, primarily because the ones installed in the electrical room, which is outside the residential dwelling unit, are circuit breakers used as tested under 60947-2. So these are molded case circuit breakers. Sometimes in main electrical rooms, there are air circuit breakers. And then, of course, the miniature circuit breakers for the units. On the other hand, if selectivity is achieved, fault is contained within the residential units. In this case, the user can reset the circuit breaker to restore power. However, if we use a 60947-2 circuit breaker within a residential facility, uh, there may it's not that there may be some hazard, but the the circuit breaker under 60947-2 standard and not tested under 60898-1 standard is not tested for non-trained personnels. So basically, you'd need a trained personnel to reset or to operate the circuit breakers if we use a 60947-2 circuit breaker within the residential units. So again, this is one of an example of a selectivity table. So MCCB to MCB, as you can see, we have a Tmax XT circuit breaker upstream, and an MCB is 800. You'd see that there's a letter T here, which shows a total discrimination between the Tmax and the MCB rated at 32 amps. So these are available via the selective optimized coordination website that we presented at the beginning of this month. And this is another one. So MCB to MCB coordination. So it's good to understand how to optimize the selectivity between two miniature circuit breakers. So as you can see, there may be a problem in total discrimination, but the idea here is that we should understand which to use in order to achieve the even at least partial discrimination between miniature circuit breaker and between two miniature circuit breakers. So let's move forward with specifying miniature circuit breakers. So here are the typical information needed. Again, we need to understand which standard we will use depending on the location of the facility, or depending on the location or where we will install the miniature circuit breaker. So we have the 60947-2 and we have the 60898-1 standard. And of course, we need to understand the electrical parameters. So as you can see, here's the under IEC 60947-2, we have the ICU, the ICS, the ICM, the operational voltage, and then the maximum power frequency recovery voltage. So as you can see, here's the test sequence. So for ICU, it's open, time, close, open. So the T is time. I think it's 3 minutes. On the other hand, for ICS, you are able to open it, you are able to close it again, operate it again, and then another time for operation, another time for clearing. So open 3 minutes, close, open, another 3 minutes, close, open. So this is the test that we use or that we do for to attain service breaking capacity of the IEC 60947-2. So these can be computed based on the IEC 60909, which was also conducted as part of the webinar series conducted by my colleague, Engineer Tristan Ocampo. So you can revert back to that webinar. I think we have a video recorded in the ABB website to refresh ourselves which how to compute for ICU, ICS, and the ICM. And another one would be the IEC 60898-1. So again, we don't use ICU, we use now ICN, which is the short circuit capacity. Pretty much the test sequence is the same, but the service short circuit capacity is based on the K factor that I've shown earlier. And of course, the operational voltage and the maximum power frequency voltage. So another difference between the two is the Umax, or the maximum power frequency recovery voltage, which is 1.05 times the rated voltage for the IEC 60947-2. And for IEC 60898-1, it's 1.1 times the rated voltage. So then, of course, the nominal current should be higher than the current passing through the circuit breaker. The breaking capacity should be higher than the prospective short circuit fault within the bus. So in this case, IK should be less than the ICU or ICN. And of course, for the Philippines, we use 60 hertz for frequency. So we need to check all of these in the markings of the circuit breaker. If it's 60 hertz, 50 hertz, if it's compliant with 60898-1 or 60947-2. And then we need to check and verify if it's more than the prospective short circuit fault calculated by our PEs or by our electrical engineers for that panel. Of course, the number of poles is important because the short circuit fault or the ICU and ICN varies depending on the number of poles. And of course, it's also good to check the electrical and mechanical endurances. So electrical and mechanical endurances, usually it's based on the number of opening and closing operations of the miniature circuit breakers. So some may be less, or some has a higher mechanical and electrical endurance than other brands. So it's something that you can check and validate to compare circuit breakers or miniature circuit breakers against each other. So you'd see why this circuit breaker is expensive than this one, or why this is much better than this one. So it's something that's worth to look at. So again, in time current selectivity, or in specifying miniature circuit breakers, it's also good to understand the tripping characteristics diagram. So in this case, we have the the logarithmic scale. So the x-axis is for the time, and the y-axis will be the multiple of rated current. So again, you need to understand first the conventional uh, non-tripping current, and then the conventional tripping current, which is the second the upper curve. And of course, we need to see which is the tripping area and which are the non-tripping area. And this is the tripping zone or the detection zone. So for example, an overcurrent of 3.1 times the nominal rated current. So you'd see here, there's a line. So 3.1, so it will trip at 2.1 milliseconds, between 2.1 milliseconds and 2.1 seconds and 40 seconds. So for bimetal protection, good overload protection, as stated earlier, it's three times the rated current, which is initially the test current for B curve circuit breakers. So here's the cable. So the bad short circuit protection primarily because it's uh it's on the overload protection zone, but if we use the electromagnetic treating device, which is in this one, we can see that the cable or the copper cable will be protected during overcurrent in this case. So the overcurrent of 3.1 times I to the times the rated current, and overcurrent of 6 times I to the of the rated current is shown in this tripping characteristic diagram. So a good short circuit protection immediately breaks during short circuit. Basically, as mentioned earlier, breaking time should be as fast as possible. So for ABB's miniature circuit breakers, it's usually around 2.5 to 3.5 milliseconds. So this is the cable. So for the tripping characteristic diagram, according to the IEC, so we have the B curves, the C curves, and the D curves. And we have another two, which is used for more sensitive circuits, which is the Z curve and the K curve for a more rugged, more transient heavy protection, which is the K curve, this one. So as you can see, the marginal characteristic measured in cold status is this area. And the instantaneous is here. And for K and Z curve, which is only under IEC 60947-2, because as mentioned earlier, for circuit breakers under 60898-1, it's only applicable for, it's only set at B curve, C curve, and D curve. So for other curves, especially for K and Z curve, it's already tested under 60947-2. So it's, as you can see, for Z curve, for Z curve, this trips much faster, while for K curve, the 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 tripping is much higher and much you call this on the higher side of the tripping curve. So the difference is that for Z curves, the C curve can protect cable 67% longer than with B curve. So Z is available for nominal for rated current more than 0.5 amps, while B curve is available for rated current more than 6 amps. And it's usually used for control circuits with high impedances, voltage transformer circuits, circuit measurement, and semiconductor protection, primarily because of the low short circuit interrupting time. On the other hand, for K curve, as you can see here, so for C curve it's in between 5 to 10. For D curve it's 10 to 20. For K curve it's tested at 10 to 14 times the nominal rated current. So basically, this is used uh, for operational safety when current peaks occur and offer quick tripping in the case of short circuit. So these are usually used for high transient application, but with the same short circuit protection as the D curve. So some of the few things that we need to check as well for miniature circuit breakers, of course, the contact position indicator, the approvals in the dome. Again, one of the more interesting qualities of ABB's miniature circuit breaker is basically the halogen-free thermoplastic enclosure, the laser printed labels, of course, the installation and removal, and IP20 finger safe terminals. Okay, so again, as mentioned earlier, miniature circuit breakers can be used both in industrial, commercial, and of course in residential facilities. And it is widely used globally, depending on what particular area you are. You can use either any of these circuit breakers. So you can get in touch with any of our sales representatives or agents or partners to get a hold of these circuit breakers. If you have any questions, you can get in touch with us or the product marketing team, and we'd be more than willing to assist you on your queries. So again, thank you so much. I do hope that you've learned, you've been refreshed on what a miniature circuit breaker function, on how a miniature circuit breaker functions. And I'll be giving you back. I'll be giving you guys back to Miss Barbs to facilitate the question and answer. Miss Barbs.
Rob, thank you. And it's really good that we don't have any technical glitches for this session. I'm very happy with that. You came off, it's very clear together with your presentation. So while we allow you to take your breath, let me just browse through the questions that was posted here in the Q&A, and some of you guys have sent also questions to me personally. Okay, let me just flash something for you as I have promised a while ago. Okay. Okay, let me just share this with you guys. And I know I have the email address of our tech pro here, so let me just share it with you. Here you go. You should be seeing their respective email addresses right now, so that if you have any further concerns, you reach out immediately. Okay? So at this point, let me just read out some of the questions for you. Okay. The first question is, okay, why is there a dedicated MCB for DC application? I hope I got the question correctly. Why there is dedicated MCB for DC application?
Hello, do I answer that or to start? Okay, I'll answer that. Yeah,
Okay.
okay. So for DC applications, there are basically the standard specifies that it's applicable for 60947-2, both for AC and DC applications. Primarily, it's used most of the time for renewable energy, for solar, residential facilities, and then in some cases it is also used for railways, for train stations, wherein there's a control signal or a control circuits the within the panel boards. So it's basically used for DC and AC. But for IEC 60898-1, DC is not tested. We have another standard for IEC 6089 for DC for IEC 60898. So it's basically IEC 60898-2 for DC application. But for IEC 60947-2, it can be used for both AC and DC.
Okay, thank you, Job. The next question is, in the Philippines, what is the standard used for testing low voltage circuit breakers? What tests are conducted for circuit breakers? So, the two questions siya, Job.
Well,
Standard.
actually, if you explore the Bureau of Philippine Standards, basically the standards governing circuit breaker, consumer goods circuit breakers. So it's both. It should be both tested at 60947-2. And recently, I think they're already exploring to regulate IEC 60898-1 circuit breakers as well. So basically, here in the Philippines, we have a testing facility, I think, owned by the Bureau of Philippine Standards to do it. So it's basically based on 60947-2 at the moment.
Okay. I have an interesting question here. He's asking I think he's asking the technical lookout when selecting MCB as overcurrent protection.
Sorry?
What is the technical lookout when selecting MCB as overcurrent protection?
Technical lookout? Saan siya makikita, Miss Marbs? Hindi ko mabasa yung question.
It was sent to me personally. I hope I got that question right, because the statement is the technical lookout when selecting MCB as overcurrent protection, question mark. Or perhaps
Well, basically,
sige, go ahead.
sorry. Well, basically, Miss Marbs, the miniature circuit breakers are usually used for overcurrent protection talaga, Miss Barb. So, what we need to see is that what they need to look for is basically the location. Of course, we need to understand if it's going to be located within a residential dwelling unit or outside the residential dwelling unit. And at the same time, the rated current, the typical electrical parameters. And most importantly, it should be the ICU or the ICN should be higher than the prospective short circuit fault that's been calculated during the power systems analysis.
Okay. The next question is, why do consultants base the selectivity analysis on ICS? And why for standard MCB or even MCCB, the ICS is lower than ICU?
Well, as mentioned earlier, we need to qualify which standard we are following. But basically, ICS is the service breaking capacity. It's also a good reference, but most of the time I understand is that the reference is the ICU, which is the ultimate braking capacity, which is the basically the counterpart of the CAIC rating of the UN. So basically, the idea is that when choosing which ICU or ICS, it should be higher than the short circuit prospective fault. On the other hand, the difference between the two is that the service braking capacity or the ICS uh, is based on the percentage of the ICU. So it's reference on the short circuit braking capacity of a circuit breaker. So you may see, you would see in the specifications that there will be 100% ICU, which means that the ICU is equal to the ICS. So basically, it just implies that the circuit breaker can be used 100% after a certain fault. So there are instances that a circuit breaker would have a 75%, or 50%, or a 25% multiplied by the ICU. So it just shows us how durable the circuit breaker is on in cases of after fault operation. So basically, it's also a good reference in doing coordination or doing selection in selecting the proper circuit breaker for the panel board.
Okay, great. So before I proceed to the next question, I'm posting right now the link to our Fab Pop Quiz so that all of you can have a visibility on it and can click it and check it out later. Okay, so let me read to you the next questions. Is ICS equivalent to 100% ICU available for miniature circuit breaker?
Uh, Hello.
Go ahead, Job.
Yes, sorry. Uh, yes and no, depending on the standard. Depending on the standard. Again, if we are using IEC 60898-1 and it will be installed in residential dwelling units, as you see, the K factor is 1 for 6 kA and below, and 0.75 for a certain value, and another 0.5 for 10 kiloamps and above. So it would vary depending on the standard and depending on the K factor of the circuit breaker. But yes, it is applicable. But I'm not sure why you need an ICS, 100% ICS for residential facilities.
Okay, next question is, technically, why does MCB does not have a trip position in its toggle?
That's actually one of our questions. We'll let you know, sir, once we find out, sir. That's actually one of our questions as well, sir.
Okay. Next question. I'm sorry, but we can only accommodate this last question. Please post if you have more questions. And what I'll do is we'll have it compiled and we'll ask our presenter this afternoon to have it answered. And we will share it together with your webinar certificates when we have it sent out to you. Okay? So let's have one more question. Have I asked this already, Job? What is the standard used for testing low voltage circuit breakers? Oh, yes, I've already asked this question. Yes, the next, let's check. Why there is a, what I think the question is, why is there dedicated MCB for DC application?
Well, actually, I already answered that, Ms. Pops, I think, earlier.
Yeah.
It's primarily used for, sometimes it's for railways, it can be used for photovoltaic facilities, for EV charging stations.
Okay. If you need a clarification for some of your questions, just please post it here in our chat group, and we will have it included in the list of questions that will be answered by Engineer Mayo. Okay? So at this point, Job, thank you so much, and to the rest of our panelists this afternoon. And thank you to our audience for joining us in today's session of ABB Philippines webinar series. So again, we're inviting you to please join our Fab Pop Quiz. I'm sure you'll find it very, very easy. So unahan na lang po, first three correct submissions will be considered, as the winner for this afternoon's session. Every webinar we will be giving away those limited Formula E cars. So you just check out our Facebook events page and our Facebook page to see if you are the one who won this very handsome package. Okay? So again, please do watch out for the lineup for September. It's going to be another exciting lineup of topics, we assure you. And we thank you for joining us again today. And please enjoy the rest of the afternoon and keep safe, everyone. Maraming salamat po. Have a good day.